In this video, we will talk about how we can prove divisibility rules using mods. So this is one of the really, I think, cool, nice applications of mods. They can help us show some of these divisibility rules that we learned in elementary or maybe middle school. So recall some of these rules. So, if I'm trying to check if an integer n is divisible by some integer a, like for example, if I'm dividing by 2 and I want to check if my number is divisible by 2, well, my number's got to be even. And the way I check that is the last digit of n even. The rule for divisibility by 3, we might remember, is that the sum of digits in my number n needs to be divisible by 3. So if I add up all the digits, that's got to be divisible by 3. Or the divisibility rule for dividing by 4 is that, well, if you look at the number that you get just from the last 2 digits of n, that's got to be divisible by 4. For divisibility by 5, well, my number's got to end with a 0 or 5. And these divisibility rules continue, but these are just some of the first few. So as an example of where we use these is 512 divisible by 4. So let's check this using my rule for divisibility by 4, which says, look at just the last 2 digits of my integer. So the last 2 digits of 512 are just 12. Well, yeah, and 12 is divisible by 4. 12 is divisible by 4. And because that's true, the answer should be yes. And I could check this, and I could do the division. It turns out 512, if I divide it by 4, ends up being an integer. It ends up being 128 if I did check it. But this divisibility rule gives me a quicker way to determine that. All right, is it divisible by 3? So let's check that out according to this rule. I got to check that when I add the digits together, 5 plus 1 plus 2, well, that gives me 8. But unfortunately, that is not divisible by 3. That is not divisible by 3. The sum of the digits is not divisible by 3. So that means the number 512 that I started with is not going to be divisible by 3. So no, 512 is not divisible. I'll just write divise, not divise by 3. Okay. So let's prove now this divisibility rule for 3. So I want to prove that an integer n is divisible by 3 if and only if the sum of its digits is divisible by 3. Okay. So let's talk about what the proof would look like. So I'm going to start off by letting n be an integer. And I'm going to write n in terms of its digits. So let's say that n, let's say that like the units digit, I call it A0. And then the tens digit was A1. And then I had A2 and then ... And the very first digit, I'll call it AK. So I don't know how many digits total n might have, but let's just label them like this. A0 up until AK, where this k, this subscript, has to be greater than or equal to 0. Okay, so there might just be one of these digits, there might be 6 of them, there might be 100 of them. Okay, and these AIs, each of these digits needs to be an element of the set 0, 1, 2, up until 9. And that's just saying that, well, the digits can be any value any integer between 0 and 9. Okay, and now I'm going to make clear that, well, that's true for any of these. That's true for any of these AIs. And the way I say that is for all integers I, such that I is less than or equal to the smallest subscript is 0 and the biggest subscript is k. This is how I indicate, well, this is true for any of these digits. We're saying that any of these digits have to be an integer between 0 and 9. Okay, so here's what I'm going to do with this. If I can write my number in terms of the digits, as an example, to get a feel for this, suppose n was 8,636. So I can break this down in terms of the digits. N would be 6, my units digit, plus the tens digit, which is 3, multiplied by 10. So that's added, we're adding 30. The next digit is a 6, but that has to get multiplied by a 100. so that it gets in the 100 spot. And then the last digit is the 8, and that's going to get multiplied by 1,000. That's going to get multiplied by 1,000. Okay, so in terms of how I'm labeling my digits up here, my A0, my units digit, is 6. My tens digit is 3. My hundreds digit is 6. And the 1000s digit is 8. All right, and I'm going to further simplify this a little bit more. The 100 is 10 squared. The 1000 is 10 cubed. And then this 10 would be 10 to the 1. So more generally, if I do the same type of thing for my n, I'm going to go back to the general situation here. This is just one specific example. So I'll put a little thought bubble around this one specific example. Okay, I'm going to do the same type of thing with my n. I'm going to write n as A0 plus A1 times 10 plus it'd be A2 times 10 squared, and then plus ... up until AK times 10 to the k. Okay, so we have this. All right. So I mentioned at the start of this that we're going to do this using mods. And we've seen that mods are just so useful when we have proofs involving divisibility. But what mod are we going to use? Well, there's two ways to kind of see what I might want to study this as. Like, I know in the problem it says I'm testing for divisibility by 3, so it probably suggests I'm going to do mod 3. But what if I didn't know that, like, I was testing for divisibility by 3? Like, what if I just decided to study this thing? Well, one of the things I notice about it is when I think about the number 10, 10 is very simple in terms of its remainder if I look at its remainder in mod 3. Like, in mod 3, it's congruent to 1. It's got the same remainder as 1 when I divide by 3. So that's another indicator to use mod 3. Okay, so doing that, if I do that and I take the n, if I take the formula that I have for my n here, we get that n is congruent to A0 plus, let me just rewrite this to move the coefficients in front, 10A1 plus 10 squared A2 plus ... plus 10 to the k times AK. And this whole thing I'm looking at in mod 3. All right, and now I can use the fact that I know 10 is congruent to 1 mod 3, which will let me replace all these 10s with a 1. And that makes this super nice. So this is going to be congruent to A0 plus, we'll replace this 10 with a 1. And then I get A1, replace the next 10 with a 1. So I'll get 1 squared, B2 plus ... plus that last 10 with a 1. So I'll get 1 to the k, AK, mod 3. Okay, but all these powers of 1 are just 1. So this just becomes, this is congruent to A0 plus A1 plus A2 plus ... plus AK, and this whole thing is in mod 3. So what we've just shown, if I think about where I started, was we had n, and we did some manipulations, and we showed n is congruent to A0 plus A1 plus A2 plus ... plus AK in mod 3. That's the same thing as saying that n and this thing, which is the sum of its digits, have the same remainder. They have the same remainder when divided by 3. Well, okay, if that's the case, that means for n to be divisible by 3, it would have to be congruent to 0. Well, if n was congruent to 0, this thing, the sum of its digits, it's going to be congruent to 0. But that's precisely what it means for the sum of its digits to be divisible by 3. And that is exactly what we wanted to prove. Okay, so that completes the proof. One thing that I want to mention about this is, technically this was an if and only if statement, which means, well, there's two directions to show. So, well, did we do both or did we just do one? So I'm going to notice that all of the steps that we did in this manipulation, all of these steps are reversible. Oops. All of these steps are reversible because of the congruences. So because of these congruences, so if I started with this, I could take it up to this step. Or if I started with this, I could take it down to this step. So it works both ways because the congruences work both ways. Okay. The other brief comment that I want to end with is many of these divisibility rules can be tackled in similar ways by investigating my integer in terms of a particular mod. And while it won't always simplify quite this nicely, like it did when I did mod 3, often there are similar types of simplifications we can make to derive these divisibility rules. And that's just really speaks to how powerful these mods are.